Yeah, doesn't seem big. All right. All right.
Are we? Hello, science lovers. Nice to see you again, or be here. Well, you can see us at least. I was here for the service, the first service in which people were available at. Oh, you got a little noise coming in through there.
Yeah, I got to turn down my volume.
Okay.
All right.
We'll start again. I know that we're talking about the James Webb Telescope today, and we're here for the first service, which was nice. And Joe Gaino was here and said he was going to have to hurry home so he could get all the telescoop.
Telescope.
Telescoop.
I see.
The scoop about the James Webb Telescope.
Oh, I see. Okay.
It's the telescope we're going to be giving you today. And I have talked about it, called it Things We've Never Seen, because that's basically what we're going to be finding out. Wanted to introduce you to it a little bit. Maybe you've seen some things about it, and maybe you haven't. But interesting questions, and I hope we get into some conversations about it, Scott. One thing is there's a video, about a 15-minute video, I think, that covers a lot of interesting things in it. I apologize, it has something like a 40-second, 35-second commercial in the middle of it that I wasn't able to excise, but we'll play that through. It's a commercial for an interesting science-related topic, though, so we'll go from that. But I did want to say that some of the things, even the artist's conceptions and things that you'll look at in some of these pictures may not be accurately true, and I'll try to point some of them out at times. Don't know if you can see something that's inaccurate or misleading about this right now, and I wanted to bring it up to show. Scott has a computer here, and you can feel free to type in any comments or thoughts as we go on, and he'll respond and get the questions or input out to me, and we'll go further. This one, what I don't like about this picture is it, for artistic purposes, it has the view of the James Webb Telescope, which maybe, hopefully you've seen some pictures of and heard some of the amazing stories about. But really, the sun is in the wrong position in that place, because really the sunscreen underneath there that looks like a big trampoline mat or whatever should be facing directly at the sun, and we'll talk about that when we talk about the Lagrange point in a few minutes. But really, this thing has to be so kept away from temperature and heat, and the sun is obviously a great resource for heat, and so that should be in a different orientation with the sunscreen there in its place, shielding the telescope function itself from it all. So we'll go on a little bit. Here's another picture of it with the sunscreen a little bit more extended out. You can see some things about it. We'll talk about the navigation, the steering on it a little bit, and the solar panels, which need to be on the side opposite the telescope itself, and some of the actions of that. So mainly I'd say that there are some reasons, basic, beautiful, challenging reasons that mankind has been able to put this telescope together. They're trying to get answers to some certain questions. And one is that the James Webb Telescope will help us find out, really, how did the universe begin? It'll move us along closer towards the answers that have so far seemed to lead towards a Big Bang and then rapid expansion of the universe. We'll be able to look in further. We'll talk again about why that is and how that is that we do that. When did the first stars form and how? We've got theories now that will probably be fleshed out and illuminated, you could say, as we go further in talking about this and as we get data back from the telescope.
It's a hot topic for an infrared telescope.
Right, right. And another big thing is it's going to be looking at and seeing if there's signs of life on other planets. I may say this a few times. This is an infrared telescope that has a capacity to look at things with some level of visible light, but mainly in the infrared schematic. We'll talk about the benefits and drawbacks of all that as well too. But it has the precision, the accuracy of being able to detect the heat of a bumblebee's movement at a distance equal to the moon. If there was a bumblebee that could survive on the moon, and this was the distance from the moon to the Earth away from it, this telescope would be able to detect that activity of a bumblebee flying on the moon. So that's just pretty amazing. So it's very likely, we could say it's possible, but it's highly likely that this James Webb Telescope will be really the latest, will be looked on later as really a turning point in humanity's efforts to understand the universe. The things that it should be able to give us with its accuracy, with its depth of field, with its capacity to look back in time and look far out in space, should just completely alter at least a lot of our views, and our efforts to understand the universe are going to be greatly enhanced. So it's very exciting and very worthwhile. This is showing where it is and why. You can see the sun in the center of this picture. The Lagrange points are mathematical, physical points in space that move as orbits change and so on. But you can see the sun at the center here, the Earth out in the right side of your screen, and then an L2 point is the point at which the the James Webb Telescope is. You can also see the orbit of the moon. The James Webb Telescope is about 1 million miles away from the Earth right now, which is about 4 times the distance of the moon. So this is a little bit out of scale, but it's illustrative. And you can see the orbit of it is going circularly around as it stays in orbit, in position with the Earth. So as the Earth goes around the sun, it hits many of these, the whole full circumlocution of the sun. The L2 point moves around with it, but the the James Webb Telescope will be moving in a circular location, almost perpendicular to it, which keeps it in a very effective location. The big effectiveness is if you'd have to say, and it's a pretty simple question, what are the 3 most brilliant lights in the sky?
Yep, I can imagine that they're all in that picture there.
Right. The sun and the Earth and the moon are the 3 largest influences of pushing light towards any feature in that area, and all 3 of them are not the purpose that the James Webb Telescope is up in orbit around there, and so we want to minimize and keep them away. At the L2 point, you can imagine that if the sun shield is pointed towards the sun, it will also shield off and filter away the effects of the heat of the Earth and the moon as well. So that's its function, and it'll be able to get a whole view of the sky because it'll be traveling around and keeping its sun shield faced towards the sun. This allows it to consistently, for many, throughout the course of its existence, keep taking pictures and not be affected by the light and so on of those other objects. So it's been said in some ways to be 100 times more powerful than the Hubble telescope, and it's demonstrable it is in certain ways, but it's doing different things, and you don't get much more resolution actually from this, even though the mirror is so much bigger, but it's working in wavelengths that are much different, and that gives some effect to it all too. So Hubble is only about 340 miles above the Earth, right, going around the Earth. And why did we send this thing 1 million miles away? First of all, you can use less energy. You maintain a stable orbit with a lot less use of fuel, and it keeps the sun, the moon, and the Earth all and always on the shielded side of the telescope. You're a pretty good astronomer. Can you say what you think will be the biggest impact on the James Webb Telescope?
Not sure what you mean by the biggest impact.
Biggest light impact, the biggest amount of light coming in towards its mirrors that will affect its.
If I had to
ability.
guess, I'd say maybe the zodiacal lights.
Okay.
That's light from the sun reflecting off of dust and debris in the plane of our solar system.
Okay. What they're saying is the biggest impact will be Jupiter,
Oh, okay.
which isn't a gigantic amount of light, and you can't shield all the light out.
Yeah.
But Jupiter will have the biggest detrimental effect on its light gathering capabilities.
So it shouldn't look right at Jupiter. It could
Right.
blind it.
It could go blind.
Yeah.
So, let's talk about now that we see to an extent why it's in that point and the energy it took to get it there. It should be able to last there with a minimum amount of energy usage to maintain it in a fairly stable orbit and a very precise rigidity and manner to it that we'll see some information about as well too, that will allow it to take very clear, very focused pictures of all parts of space. But let's look at some of the components and what it does. If you can see, the big thing that you're probably aware of and seen a lot of talk about are those primary mirrors. They're 18 beryllium, which is the lightest metal in the atomic scale, covered with gold. Not a lot of gold, but enough gold, and gold is they'll talk about again what is going on with that. Why it's there. Scientific instruments are in the back side of that, of the telescope, of the mirror there. You can see out in front, it's extended, and it's done this successfully, a secondary mirror that allows it to act in the ways that most telescopes need to do to focus light and bring things in. Down at the bottom, you can see the stabilization flap that allows it to correct its course and keep stable in space. The antenna and the solar panels are going to be faced at the Earth and at the sun so that they'll get proper capacity to communicate with Earth and will get solar panels for energy and power. And in between all that are those amazing sun shields, which had to be all folded up inside a rocket, shot up into space, and then unfolded. 5 layers of sun shields on here, which keep the top of the telescope, the mirror, and all the scientific instruments up there at an amazingly cold state. If you're familiar with energy and temperature and so on, people in space usually use the Kelvin scale, which starts at 0, absolute 0, when molecules are completely immobile. There's no energy in a system, right? So 0, absolute 0. This top side of this, the scientific instruments, this whole area here will actually be at somewhere around 30 degrees Kelvin. Now, it's the same as the centigrade system, the gradation between degrees. It just starts at a different amount, right? The people that are talking about low temperatures don't want to talk about the centigrade or Celsius scale. They just started at 0 when there is no energy in a system at all. So if you're at about 30 or 35 degrees on this scale, you're extremely cold. You'd have to get up to somewhere in the
73 is
273 is freezing, or okay.
water freezing. Yeah.
Water freezes at 273 degrees. So this is very, very cold. The bottom side of this, facing the planets, is a whole different thing. The sun shield with the 5 layers of metallic plastic keep that temperature, if I see it well in my notes here, that can be up to 180 degrees, I believe. Yeah. So that side is going to be very hot. The first 2 shields, first 2 layers of the sun shield will be very warm yet, but by the time it gets up to the top, through the fifth layer, you're going to be down at very, very cold temperatures. And we'll talk about a little bit of why that is too. The primary mirror is somewhere around 21 feet across and has 18 miniature hexagons that meld together. And I think the video will talk a little bit about that. Another thing that's interesting is the construction of this and the planning for it started in 1995, which was the first year that any exoplanet was seen by telescopes that we had at the time. We surmised, we thought that they were there, but it was the first discovery of exoplanets. And that's one of the main goals of the James Webb Telescope. So there's kind of some epochs of things, of the exoplanet system. Finding one or two exoplanets back around 1995 was kind of epoch one. Searching and saying, well, this star has a little bit of wobble in it or whatever, and we may believe that there may be some planets rotating around this. But then it got to be much more capable with Hubble and some other Spitzer telescopes and so on that were able to do some of these things. And so there's a second epoch that the Kepler, I think, Space Telescope was really developed to check the exoplanets. And at that time, in epoch two, in the early 2000s, we were finding dozens, once in a while hundreds at a time, of exoplanets all around the universe. And now we're at the point where, even though this was started being built in 1995, it has the capability to bring us into epoch three. And epoch three is really going to be studying exoplanet atmospheres. So not only do we know where many exoplanets are, but we're going to be able to study what makes them up, what they're comprised of, if they're in the Goldilocks zone, if they're in areas that are not too cold and not too hot and allow for potential life. They'll be able to check for water and check for a lot of different signs that may indicate life on planets that are hundreds, if not thousands of light years away from us.
As I understand it, one of the primary targets, early targets, is going to be the TRAPPIST-1 system. Are you going to talk about that? Yeah.
I think you should.
Yeah.
The TRAPPIST-1 is a pretty interesting system, and if you have some information about it, or...
Yeah, I was just looking it up on Wikipedia as you were talking. The TRAPPIST-1 system, I think it has 5 or 7, I may have the numbers a little off, but something on the order of 6 Earth-like planets.
all rocky planets.
Right, that orbit this star, and
It's a very
40 light years
old
away.
red dwarf star, so
Right.
it's a much smaller, puts out much less heat than our sun. And these are much closer to this sun as well, too. But we were still able to identify them as, 6 varying planets. I mean, just the capacity to detect them when they're that close to the sun is amazing, I think.
Right, and so all of those planets, all 6, 5 or 7 of them, however many it is, are going to be early targets for the telescope to gaze at, and hopefully it'll figure out whether or not they have atmospheres,
Right.
at least, and
Right.
then if they do, what's it made of?
Yeah. And we'll talk about how they do that in a little bit as well, too. The James Webb Telescope has somewhat of a finite lifespan. It needs fuel to do a lot of the things that keep it in exact position, so it's making constant adjustments, something like 16 a second adjustments to fine-tune its positioning. And so that's, and some actions about how to keep the thing as cool as it needs to be as well, too. So there are some fuel responsibilities, and they're thinking that depending upon how well they can monitor it and how well they can keep it working properly, 10 years, maybe 20 is the lifespan that they're planning for it. It's not serviceable, at least not now. Who knows what it'll be in 20 years. But because it's 1 million miles away, so it's got it would have some pretty challenging things. You may remember that the Hubble telescope had a a focusing problem. I think that their mirror, which is I think 21 inches across, was off by out of focus by about the width of a human hair at the edges, and that caused out of focus images. And we were able to send up a crew in one of the space shuttles who then put on corrective lenses onto that telescope and fixed it up. So,
Bifocals, yeah.
right. So, so that's some of the aspects of its positioning, but you might want to wonder how it can do these things. This is showing the different wavelength spectrums that 3 of the different telescopes that have been put up into space, the realms in which they perform or work. You're obviously familiar with the Hubble, and if you can see there, it worked a lot in visible light spectrum, a little bit in the ultraviolet spectrum, and a little bit in the infrared spectrum, but not much at all. On the other hand, the Spitzer was almost completely, if not completely, in the infrared spectrum. So a lot of things were discovered.
Yeah, long wavelength infrared, so
Right.
deep infrared.
Right. And the Webb is somewhat in between the two. Although this is another point I wanted to bring up. This is pretty misleading too. I think that maybe people wanted to show, it looks like the Webb has this phenomenal range. It goes all the way from one to the other, covering all the bases. If you really look, it's 0.6 microns to 28.5. And that, if the infrared spectrum goes up to about 180, like it shows there on the right side, so 28.5, it's only covering really 22 microns in the spectrum, right? And so it's not as thorough as in the infrared spectrum as it looks here. And actually, the Spitzer telescope goes down almost as low in the infrared spectrum as the Webb does. So the Spitzer has a wide 150 micron wavelength. Okay, and so there's actually some misleading things in there, but it gives you a picture of what it's trying to look from. Okay, and so, like I said, this can detect the heat of a bumblebee flying on the moon. The UM is microns, which is 1,000th of a millimeter, okay, is the wavelength of these. And just, so that means it's 10 to the minus 6th of a meter. A meter is somewhere around your span, a little bit past your span of your one arm. So it's a millionth of that. My closest work at Sedwell with people that were grinding, fine grinding and so on, is about 5 microns accuracy. So if you see this working there, we can do some of these as we just take off tiny sparks of material and on a grinding wheel at Sedwell, we can be about 5 microns accuracy. So that gives you some idea of the width, the length of these wavelengths of these different waves.
And it reaches a little ways into what we would call visible red.
It does.
Right.
It does, right.
And that's really interesting because a lot of, when you see pictures in books from things in the sky, astronomy pictures, you'll see a lot of red nebulae and red clouds of gas and whatnot. And so that's because hydrogen atoms, one of their easiest excitation levels is a deep red color. So this should be able to cover that as well as beyond that to just thermal emissions as well.
Okay, neat. So you kind of wonder what an example might be with some of these different telescopes and what you see and what's the value of seeing in the infrared. You'd like to see what we see, right, is a kind of a common human thought. And here's an example of that. This is one of the famous pictures by the Hubble telescope and it was named the Pillars of Creation. It's in the Eagle Nebula, and it's also M16. And so it's an amazing picture. It just looks like grotesque figures standing in space or something like
Beautiful
that.
figures.
It's beautiful.
Beautiful
yeah.
figures.
Beautifully, yeah, yeah. And so it's been nicknamed the Pillars of Creation, and that's what the Hubble telescope was able to come up with. But it scientifically has some weaknesses. You can't find out a lot about space when you're seeing a picture like this. It's hidden and covered. A lot of what you'd like to see is really covered by intergalactic dust. So the Webb, looking at infrared, and I've got a picture of an artist's impression of what they will see, although and compared side by side with this picture in my next slide. So if you look at this slide on the left, the Hubble telescope picture in visible light, and then you look at what you can see in infrared light, it is able to blast through much of the cosmic dust and actually pick out areas in which stars may be being created, and a whole variety of different very interesting occurrences, scientifically interesting occurrences are taking place. So that's an infrared view of the same picture.
You'll notice also that you can see many, many more stars
Right,
in the infrared picture.
right.
So that those pillars there of gas and dust are blocking the light of stars both embedded in them and more distant.
Yeah.
If you look on a computer or find this picture yourselves, you can see even a couple of galaxies in the far distance that are not visible.
Not visible at all, right.
Right.
Yeah, so scientifically speaking, it's just an amazing advancement, and that's why they're saying it's 100 times more powerful than the Hubble. So what are they doing now with the Webb telescope to get it ready to start doing these things? It hasn't had the capacity yet, but they've sent it out into space. It left on December 25th, and it fairly quickly got out to its Lagrange point, and it's out there doing well now. On the way out, they extended the sun shield. They opened up the primary area of the mirrors, and then they opened up the wings that go on the side of it, all successfully. They then extended the secondary mirror to get into that area. But it's out there in space, and it was stowed for shipping along on a rocket, obviously, to get out to that point. They had to release certain controlling bolts and so on that allowed it to do those things. And now that it's out there, it's doing two main jobs right now. One is, you may have heard of, is aligning the telescope. But the other is just this thing I mentioned earlier, cooling the apparatus. Mm-hmm. Just phenomenal efforts to try to get this. And because it's in infrared is how we detect, a lot of heat spreads in the infrared zone. You can see that maybe if you're standing in a bus stop or outside a hotel waiting for a bus, and they have some infrared heaters above you generally to keep you warm. So it spreads this heat out, and the Webb telescope leaders have to get that heat isolated and kept away. And as I said, it's getting phenomenally hot on the sun shield side, but has to cool down. I had said earlier about 35 Kelvin, and one of the apparati for the scientific apparatus has to be down to 7 Kelvin.
Wow.
7 degrees above absolute zero. And so it's cooling down now is another aspect. So if we start looking at what the aligning the telescope might mean, each of those 16 individual mirrors has been working just by itself and can collect light and send it back. And very shortly on, they were able to take the picture that you see on the left. And that's a bit of a, just a capture of each of the different lights. They're aimed at the same star, but they aren't in position to combine their lights, to lay them one on top of the other. So the 16 lights there are all different ones that then they had to identify, well, is this one, you know, they code these things, A1, A2, A3, which is the proper alignment, and how do you do it? I don't know if you can see it well on the screen. I can't see it too well here, but I think they said those bottom three on the left are the one side wing, and so they identified each one, and you can see that A2, A3, A1, B1, so on. And so they then had to identify them, and then they arrayed them in a way that they can start manipulating them from.
So each one of those dots comes from one segment, one of those hexagonal segments of the mirror.
Exactly, of the same star.
And they were out of alignment by a couple of, or less than a hair's width, but it created this picture that they were sort of randomly distributed.
Right,
Yeah.
right. So with some fine tuning, they can start bringing them in, and the image that you see on the right is the arrayed image when they've put them in a place that now they can start manipulating them from. B1, C6, and B6 are the one wing. B4, C3, and B3 are the other wing, and the other parts, all the A's are the interior 6 mirrors. And they've got these things organized in a way that they can start even getting more accurate in their fine-tuning. It's amazing when you see it. I'm going to show you a video that takes, like I said, about 15 minutes. And when you think of it, they aren't talking about, haven't given you ways to compare some of these numbers, but it'll come partway through the video. When they talk about a nanometer, a nano means a billionth of a meter. So it's a thousandth of a micron that we were talking about earlier. I said at the shop we can grind to maybe 5 microns if we're on a good day. So this is 1/5000th of what our greatest capacity is. A sheet of paper like this, it's about 100,000 nanometers thick. Okay? A typical germ is about 1,000 nanometers thick.
Wow.
And a molecule of water is about a nanometer thick. So when they start maneuvering this stuff to within nanometers, think of molecules of water that they're able to adjust this to. I spent a lot of time trying to find out exactly how they're doing it, because we make pretty precision parts, but they're nothing like this. You can't, if you're going to adjust, I'm thinking of how you adjust a mirror, and it almost seems to me, and they'll talk a little bit, you can do some adjustment with really finely made screws and nuts and things that pull and push on these things, but you can't make a screw that is a molecule of water pitch on it so that you can pull and push with, you know, some kind of controlled motor. They do that to get it to a certain point, and I don't have an answer as to how they get it to the precision that they're going to get it. And I'll try to look into it, and if I get an answer, I'll report it back in a further Science Sunday. But just phenomenal. I don't know if they're doing it by correction in software, right?
Yeah, I don't know if it's electromagnetic, like piezoelectric actuators, or if it's, like you said, you know, essentially a screw or a post that moves by a very controlled amount.
Well, there are screws and posts, and we'll see them a little bit later in the video. But I don't think the accuracy of what's necessary in this is going to be achieved by any man-made item. I don't know how they did it, and
It's magic.
No, it's science, but
Okay.
it's something. All right. Let's see if I got everything. We talked about the Kelvin scale and how deep this is going. So yeah, I think we're ready to look at this video, and it's an interesting thing. If we happen to, we'll have a little bit of a advertisement for a company called Magellan, but they do some pretty interesting science videos. So you can always go back and look at that and get their address if you want. You can get a month free too if you do this.
After 20 years of development and 2 weeks of the most complex deployments ever attempted in space, the James Webb Space Telescope is now fully deployed. Even though the deployments were the riskiest part of Webb's commissioning, getting the optical system to work is equally critical. All 18 of Webb's hexagonal mirror segments must be aligned to within 10 nanometers of each other to form a single primary mirror. And that requires making ultra-fine adjustments as small as 1/10,000th the width of a human hair. This is a slow, meticulous process called phasing. It will take about 3 months to fully execute, but when it's finished, Webb will behave much like any other telescope. The telescope part of Webb is called the Optical Telescope Assembly, or OTA for short. The primary mirror's job is to collect as much light as possible. The more light it collects, the fainter the objects it can see and at higher resolution. The primary mirror has a concave shape that sends light to a convex-shaped secondary mirror. The secondary sends the beam into the aft optical system, or AOS. And by the way, this is the same structure that had that famous lens cap covering its aperture. It even said removed before flight, which in retrospect was definitely a good idea. So far, Webb's optical layout resembles the classic Cassegrain telescope design, which uses 2 mirrors to form an image. However, this image is not fully corrected. In fact, it's purposely quite blurry. And that's because Webb is actually an advanced 3-mirror anastigmat telescope. The cool kids call it a TMA optical design. This configuration sends a portion of the total image through the AOS opening to a concave tertiary mirror. The tertiary forms the final image that is fully corrected for astigmatism, coma, and spherical aberrations, all while precisely controlling field curvature. And this design gives all of Webb's science instruments an equally sharp image of the sky. Although the image is now in focus, it's still a little shaky, and that's because reaction wheels are always spinning to keep Webb on target. And this introduces residual vibrations into the telescope. That's why Webb carries a 4th mirror called the fine steering mirror. It's a flat mirror that acts as an image stabilizer. The FSM continuously tilts in the X and Y directions as frequently as once every 64 milliseconds. That's 16 tiny tilt adjustments every second. From there, the final stabilized image is sent to the science instruments. At least, that's how it's supposed to work, but we're not there yet. Webb's mirrors must operate at temperatures as cold as 35 Kelvin, and all 18 of the primary mirror segments must be aligned to within 10 nanometers of each other. But even this quick look at Webb's optical system raises some questions. For example, why does the AOS aperture and the tertiary mirror have those elongated shapes? And why does the fine steering mirror look like a miniature primary? What are those black borders doing around the primary anyway? And what's with all that gold bling? And finally, is Webb really going to be more powerful than Hubble? Well, today we're going to take a closer look at just how Webb's optics work and discover the answer to those questions along the way. But first, I'd like to thank Magellan TV for sponsoring today's video. Planet hunting with the James Webb Space Telescope shows how Webb will explore the details of alien atmospheres in the neighborhood of our sun. It's just one of more than 3,000 documentaries available exclusively on Magellan TV. New documentaries and series about nature, history, science, and technology are added each week and are presented without commercial interruption. And now, Magellan is offering my viewers a full month of their award-winning content absolutely free. Just use the link in the description of this video. Webb's complex design is ultimately driven by its science goals, which include studying the first galaxies to form in the early universe. But because the universe is expanding, much of that light is shifted into the infrared. But infrared light makes it harder for a telescope to achieve a high angular resolution. Here's why. Resolution is a measure of how small an angle a telescope can see down to and still distinguish details from each other. The larger the mirror's diameter, the smaller an angle it can discern. However, the longer the wavelength of light that the telescope is looking at, the larger the smallest angle becomes and the lower the resolution the telescope gets. The only way to overcome this limitation is to make the mirror even larger. At 6.5 meters, Webb achieves roughly the same resolution in the near-infrared as Hubble achieves in the visible spectrum with its smaller mirror. And you might be wondering, well, why then is Webb considered to be more powerful than Hubble? Well, the answer is a combination of resolution, sensitivity, and wavelength coverage. First, Webb certainly has a higher resolution than Hubble in the near-infrared part of the spectrum. And Webb's near-infrared camera actually has 16 times the pixel resolution of Hubble's Wide-Field Camera 3. Second, plunging Webb into the deep cold allows it to detect faint infrared signals without emitting its own thermal noise. And that gives Webb a much higher signal-to-noise ratio in the infrared than Hubble can achieve. Webb's large size means that its optics have to be exposed to open space in order to cool down. And that's a problem when it comes to stray light. The Spitzer Space Telescope was enclosed in a tube that blocked unwanted stray light from reaching its mirrors. But an enclosed design traps and re-radiates heat back into the tube. Spitzer solved this problem with a series of heat sinks, radiators, and cryogenic cooling systems. The bottom half of its tube was painted flat black to radiate heat directly into space. But Spitzer was an 85-centimeter telescope. Scaling that system up to Webb size would have meant having to sacrifice mirrors and instruments just to fit inside the rocket. And that's why Webb instead uses an open design to allow residual heat to radiate away. But this open design means Webb is going to have to deal with stray light very differently. The primary mirrors are surrounded by opaque borders called frills. They block starlight coming from behind the telescope from reaching the secondary mirror. The aft housing is specially shaped, or baffled, to accept only the portion of the field of view that the science instruments see. And that's why the AOS aperture has that elongated shape to it. It's actually cut to the same shape as the science field. The fine steering mirror is also surrounded by a mask corresponding to the frills around the primary mirror. And thanks to the sunshield blocking the sun, earth, and moon, the brightest source of stray light for Webb is Jupiter. Behind the sunshield, Webb's mirrors cool all the way down to between 35 and 50 Kelvin. At those temperatures, thin glass mirrors are unable to reliably hold their shape. That's why Webb's mirrors are made of beryllium. Like any other material, beryllium shrinks as it cools. But it's also very stiff, so it doesn't warp as it cools. And once it falls below 100 Kelvin, beryllium stops shrinking and becomes very stable. And that means temperatures can vary by several degrees across each mirror segment, but as long as it never exceeds 100 Kelvin, the mirror maintains its shape. With an atomic number of 4, beryllium is the second lightest metal on the periodic table. That makes a beryllium segment 33% lighter than a segment made of aluminum. However, beryllium is 6 times stiffer than aluminum and is even stiffer than titanium. To see what I mean, here are 3 levers made of titanium, aluminum, and beryllium. When they're all sprung at the same time, the beryllium lever barely shakes and comes to rest long before the other metals. And that's particularly desirable because Webb's mirrors were launched vertically instead of lying on their backs like other telescopes. Now, even though beryllium has great cryogenic performance, they and the rest of the telescope structures will shrink down as they cool. So engineers actually built all of the telescope's components and the mirrors to be a bit larger than they're supposed to be so that they'd all shrink in the cold to their correct size. And because Webb must reflect infrared light, its mirrors are coated with a thin layer of gold instead of aluminum. And that's because while gold only reflects the longer wavelengths of visible light, it's an almost perfect reflector in the mid-infrared. And then, of course, there's the requirement to fold up the mirrors ahead of launch. That's why 6 of the mirror segments are mounted on 2 deployable wings that, along with the secondary mirror assembly, were folded up for launch and deployed once in space. And we talked about the details of the deployments in our last video, so I won't repeat them here. But at the same time, why hexagons? Why not some other shape? Well, hexagons combine into a roughly circular shape, which is what you'd want when you're trying to concentrate light into a central point. Another advantage of hexagons is that they have what's called a high filling factor. And this means the segments fit together without gaps. If Webb used octagonal or even circular mirrors, there would necessarily be gaps in between them, which means the mirror doesn't collect as much light. Each segment is about 1.4 meters across. Together they create a 6.6 meter diameter hexagon from tip to tip. And that six-fold symmetry means that each mirror segment only needs to be shaped to just one of 3 different prescriptions. But the best advantage of the segmented design is that it won't repeat the same mistake made with Hubble. After it was launched in 1990, NASA discovered to its horror that Hubble could not be brought into focus. It turns out that the outer edge of Hubble's primary mirror was ground to a slightly flatter shape than it should have been. The error was tiny, just 1/50th the width of a human hair, but its effect was enormous. The result was that Hubble suffered from spherical aberration. Thankfully, Hubble is in low Earth orbit and could be serviced by the space shuttle. After corrective optics were installed in 1993, Hubble's vision was fully restored. But Webb is too far from Earth to be serviced, and it can't be returned to Earth orbit for servicing either. The good news is that Webb's telescope and its instruments underwent a full set of optical systems testing in a thermal vacuum chamber to verify that everything was fabricated and integrated correctly. This was a major lesson learned from Hubble, which never had this full optical test before launch. But if you're still not assured, don't worry, because the process of phasing is Webb's ultimate insurance policy. It begins by deploying the mirrors from their launch configuration. At full speed, it takes about 1 day to move all of the segments by just 1 millimeter. That's about the same speed at which grass grows. This is why this initial deployment alone takes at least 10 days to complete. But when it's finally done, the mirrors can then be phased together. Behind each segment, 6 actuators are arranged in a hexapod configuration. They adjust the segment's orientation in not just focus, but in 6 spatial degrees of freedom, including its pitch, yaw, and roll. They can even adjust the segment's horizontal and vertical position in space with respect to the others. Each segment is separated by a few millimeters to allow for these adjustments. An additional actuator in the center of each segment is connected to 6 legs that attach at the hexagon corners. The push-pull action is then able to adjust the segment's radius of curvature. And that means any imperfections in the mirror segments can be individually corrected. Likewise, the secondary mirror can be adjusted in a similar manner, although it doesn't use a central actuator. Webb begins its mirror alignment by imaging a star with the near-infrared camera. Initially, it sees 18 images. One by one, the mirrors are adjusted until the images are stacked in the center. That's a good first step, but the image is still going to be blurry. To really get the segments to combine into a single monolithic mirror, actuators continue to adjust each segment, this time in smaller amounts. After each tiny adjustment, the image's point spread function is analyzed. A point spread function is essentially a plot of a point source's intensity on an array of pixels. The Webb team developed special algorithms that analyze the PSF and work out just which actuator on which mirror segment needs to move next and by how much. The commands are then uploaded to the telescope, which makes the prescribed adjustment, and the process is repeated. With each adjustment, the star gets a tiny bit sharper. The sharper the image gets, the smaller the changes become. At the beginning of phasing, actuators moved the mirror edges by up to several millimeters at a time. By the final phasing, they're moving just a few nanometers. And that's just 1/10,000th the width of a human hair. But we're not done yet, because the other instruments are looking at different parts of Webb's field of view. So additional phasing is required as each instrument reaches its operating temperature. Needless to say, this is a very slow and meticulous process, which will take about 3 months to complete. Meanwhile, Webb's science instruments are being brought online as they cool to their operating temperatures. They'll run through a series of calibrations and test observations. One of them, the mid-infrared imager, has to be chilled all the way down to just 7 Kelvin. In fact, the instruments and the kinds of science they will be used for really ought to be in their own video. So yeah, there's a lot of work left to be done before Webb is ready for science. But now that it's fully deployed, most of the mission's risk is now retired. So congratulations to the Webb team, and shine on, you crazy diamond. And by the way, how about after
So I thought that was a pretty nicely videoed demonstration of certain things. It would be tough for me to pull everything together to talk and show all the different aspects of the Webb telescope. They don't spend a lot of time on the instruments on the back, and but they are kind of the heart and soul of the machine. After the light is collected, then you have to manipulate it and test it and try it out in many ways. So the question gets to be is, what will Webb explore? What is it looking for? And this is off of a NASA website, and these are the goals that they say that they want to go at and want to explore, and I'll talk about them a little bit and show you some pictures of some of them. So they want to talk about exoplanets and planet-forming disks. Disks are the generation, the early way that planets started concreting, coming together to make a planet itself. It's just the dust and the particles out in space that start having gravitational attraction to each other and spinning while they're in orbit around the whatever star they're going around.
And those particles rub together and get hot, so an infrared telescope's a good thing to look at.
Yeah. Next is they want to explore galaxies and see the structure of galaxies and what's happening in there, these great conglomerations of millions of stars. The Intergalactic Medium, I have some pictures to show you of some of these things. Medium means just the stuff, right? The things that are out there. You can also replace it with the word dust or whatever. So the intergalactic is the dust and things in space that are in between galaxies. And they're different in many ways than the circumgalactic medium, which is the things that are out around the circumference, the outside of galaxies, and are exuded or brought back in by the galaxy itself. Large-scale structure of the universe. This is kind of the cosmological question, right? How did the universe form? What happened as close to the Big Bang as we can understand? And what can we find out about it? So that's going to be a large emphasis. Basically, people that have scientists all over the world are kind of putting in their time, right? Putting in applications for being able to use time. I don't know if I talk about it or plan to talk about it, but basically, one way they've done this is that it can take a lot of time to gather the light from something so far away. It can take 100 hours maybe to gather light, but the instrumentation that's set up on there has the capacity to collect that light and data from 100 different stars. I don't know.
Oh, at the same time. Yeah,
at the same time.
Right. The spectrographs and whatnot.
Right. So as it's doing it, it can move around and calculate and work with that, so they're getting as much data in as short a time as possible. So determining the large-scale structure. What is the universe really made of, and what is it doing? It's going on this expansion that is almost incomprehensible. It's expanding faster than the speed of light, so it may give us some answers about dark matter and dark energy and the beginnings of the universe. The next thing they talk about is just solar system astronomy. What is really the makeup of our solar system? We have our ideas and theories, but there's a lot we don't know about things beyond Pluto, the Oort belt, and a lot of the things that are there. So just the astronomy, the makeup, how the solar system itself came to be. And not just our solar system, but other solar systems of other planets, of other stars, I mean. stellar physics, the physics of stars and types of stars, how those stars are different, what makes them different, what's the life cycle of a star. All of these things we have some level of knowledge on, and some we think we have pretty clear ideas of. But really, when you talk about this, anything that comes in as data from the James Webb Telescope will be an incredible addition to the knowledge base that we're working from right now. Stellar populations. Why do stars populate in groups and in the ways that they do? And here's another one, the interstellar medium. What is that about? This is between stars, the dust and the particles that are between stars. You may have heard about solar wind and things like that. And this will be talking about some of that as well, too. Supermassive black holes, maybe one of your favorite topics, right? Black holes and active galactic nuclei. Are these, they call them AGNs, the active galactic nuclei, are they the birthplace of black holes? Are they, how does that actually come about? What critical elements have to come together to form black holes and these galactic nuclei?
But by the time, Hubble can see images or collect light from galaxies, by the time that light is in the visible spectrum, it's thought that the black holes have already formed. So looking back further in time, as we look deeper into space, because of the expansion of the universe, the light is redshifted.
Right.
So light that started out in its local environment as visible, when it reaches us in a completely different epoch of space-time, that light will, we will apprehend that light as red light or infrared light. And so the Webb telescope may be able to look at some of the first galaxies and first stars and maybe give us clues about how the first large black holes formed, too.
Right, it can capture the data that is maybe not seen by the Hubble's visible, by the Hubble's available spectrum. It'll see the things. And basically you're saying that as the universe is expanding, like I said earlier, faster than the speed of light, that stretches out the wavelengths of the light that's emanating from these stars, and they're not coming in as they were emitted, and we're more able to see them, and they come into us in the infrared or red spectrum.
Yeah, the universe stretching faster than the speed of light, that's one way to kind of look at it. It has to do with the speed of recession of things we look at increases the further away they are. And you can find analogies and descriptions of this in books and videos. But essentially, the very furthest things we can see in the universe, from our point of view, are being carried along by the expansion of space faster than the speed of light can move. And that does not violate relativity, which I'll be talking more about next time, because there's no physical object moving faster than light. It's just space itself. At the fringes, at the outer edges, look to us to be expanding faster than light. But locally, space isn't expanding in any way appreciable that we could measure.
Right, right. I know Scott's talked about it before, and when I talked about the Big Bang many years ago, kind of the concept of the expansion of space can be thought of if you have a balloon and you've taped 3 dimes onto it, or more dimes than that, dimes all over, and then as you expand the balloon, things that are fairly close to the balloon are expanding at a certain speed, but things that are farther away expand relative. You can't say that anything's staying the same. Everything is expanding, and this whole realm is increasing. So, here's some concepts that fit in with that. I know we started a little bit late because they were doing some music preparation for next week here, so I'll just go over a few more minutes. But this is an artist's conception of the intergalactic medium. Between galaxies, there's dust out there. Somewhere around maybe a molecule of dust per every cubic meter has been estimated. Wow. A molecule per every cubic meter. So we call it a vacuum, but it isn't, although it sure is darn close to one. When you think of that, the intergalactic medium then would be the set of hot X-ray emitting gases that permeate the space between galaxies. Temperatures of these things can be millions of degrees, very, very hot.
So, yeah, the overall heat energy could be low, but the temperature is high because each molecule within each of that cubic meter, the one molecule in that cubic meter is moving quickly.
Right.
So it's a hot molecule.
Right, exactly. But it's cool space, right? Because
Right.
it's so unpopulated.
Right. Yeah,
Yeah.
the density is low enough that there's not a lot of thermal energy cumulatively.
And it's actually less than one atom per cubic meter, not even a molecule. So, and they're often metals, and the source of intergalactic winds that you've heard about, maybe solar winds and so on. But they're often metals, and it's some of the things that have actually helped make planets, right? These are the things that as they're traveling around, they're emitted from stars that blew up, and this intergalactic medium, it's a very hot topic to study. And we'll be able to see things because they are hot, and the infrared detectors will be able to pick up things about it. They'll do a lot of study about intergalactic mediums. Circumgalactic mediums, slightly different, more populated. Gas surrounding galaxies, but within its gravitational control, you could say. That might be a layperson's definition of it. It's the source of a galaxy's star-forming fuel. So you can see a galaxy there with circumgalactic medium around it. They talk about wasteful galaxies, they say in this thing, and they launch heavy elements into halos and beyond. So things that escape the gravitational field probably come out to be the intergalactic medium. But all this is the stuff that, like I showed in the picture of the pillars of creation, this is stuff that interferes with some levels of capacity of looking at things that they may want to look at, and they also want to understand these objects better. This is interstellar medium. So you can see a depiction that's not to scale at all by any means of the sun on the left and the planets around it, and the edge of the solar system is hard to define exactly where it is because you keep on finding dust and particles that are further and further and further away. So we really don't know a lot about the interstellar medium and what's going on out there. If you can see, I think towards the top it shows a representation of where Voyager 1 and Voyager 2 is down below that, of where they are in space now after, I don't know if it's about 20 years of travel.
Yeah, 30 or 40.
Yeah. And so they're going out, and they're still sending back images, I believe, and they're going out to explore some of this stuff too. But the knowledge that we'll gain about circumgalactic medium is going to be interesting. About interstellar medium. So it's the matter and the radiation that exists in the space between star systems in a galaxy. On the far right side, you can see a representation of a bunch of stars, and the biggest one there is Alpha Centauri, and next to it it's a double star with Proxima Centauri, 4.2 light years away from the Earth, something like that. The closest things that would take a very long time in Earth time for us to travel and get there. But what's going on between there is much matter in between there and things to study and explain and understand. Finally, an artist's depiction of supermassive black holes and an active galactic nuclei. You can see it bringing in particles into it, and what makes up a black hole, and what can we find out more about black holes with infrared capacities of the James Webb. We're going to be studying a lot of things about them. So I hope that gave you a picture of what the James Webb is about, how it's been made, and what it plans to do. It's a fascinating topic to study and to look into, and the knowledge base that will come to humanity because of this is just a phenomenal benefit to all of us, I think.
Well, you didn't have a detailed depiction of this, but the fact that it can study exoplanets and the atmospheres of exoplanets, it can essentially figure out the gases that are present in the atmospheres of exoplanets.
Yeah.
And if it finds oxygen, and there's even been talk recently that it could spot the traces of chemical pollution from a possible industrial civilization in the atmospheres of other distant planets around other stars. So really the possibility of spectacular results, but even with the things that aren't speculative, like other civilizations around other worlds, the results that we'll get from the Webb will change our understanding of the universe. There's no doubt about it.
Right. I think that's a good point. It does that, and I probably should have spent a little bit more time talking about exoplanets because it is a fascinating and important part of what it's going to do. But it takes spectrographic readings, which means that it brings in the wavelength of light, filters it, and it sees, you can have, each element puts out different spectrographic readings. They have different bars and lines. You've probably seen something along those lines, but it puts out a specific spectrographic reading, which is how you can look at an exoplanet. You can tell whether it has oxygen or carbon or any of the different elements that make it up. We've already done that with planets, Jupiter and things like that, and we've done it further in the solar system as well too, but this will be much more calculated and carefully able to be assessed. And then the thing to think about that is, like I said, the nearest star, which definitely won't have life around it. We know that pretty well right now, but is 4.2 light years away at the distance that
And it has
light-
planets.
Okay.
The Alpha, Proxima, Beta Centauri system does have planets associated with at least some of those stars. So,
And so if we'd find out something on it, we'd actually be finding out what it was 4 years ago, right? Because it takes that long for the light to get here. Most of the planets that have, most of the exoplanets in the universe are much farther away from us, and the light takes much longer. We might find some evidence of oxygen or water or chemical corruption of the environment in some way, but it might be on a planet that's, 5,000 or 500,000 light years away. So we might be seeing what that planet was like 5 years ago or 5,000 years ago or 500,000 years ago, not what it is right now. So it's not that, it's not going to give you an actual snapshot of the exact universe, how it is right now.
yeah, and the whole concept of right now, when talking about cosmological distances, becomes a bit squishy, and that's part of what I hope to cover next Science Sunday when I talk about general relativity.
Okay, great. Well, on that note, it's probably a good way to end it. Thanks for participating. You will be able to sit in the sanctuary. There's room for 40 or so people, and you're more than welcome to come starting March 20th. We've had the first church service in the sanctuary today, and it went smoothly. So if you're willing to put a mask on and come, we'd love to have you here. I think it's so much nicer talking to a room of people than to a room of chairs.
Yep.
The chairs don't seem to be gaining any intelligence as we speak to them.
I've never heard one complain, though.
That's true. So hope you have a great day and that your March turns out beautiful. You have wonderful weather, and we'll see you hopefully in 2 weeks. So long.